The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So, good afternoon. Let's have an on-time departure. Last week, we talked about quantum states of light. So we're talking about the photon, the quantum description of the electromagnetic field. And I introduced for you the most classical quantum state of the electromagnetic field, namely the coherent state. I don't want to go through the formalism again, but the coherent state has a simple definition, simple but subtle. It's an eigenstate of the annihilation operator, and it has a complex eigenvalue alpha. And from that, you can pretty much derive everything you want to know about coherent states. Colin?
What was the purpose of, whoever discovered coherent states, what was the purpose of trying to find the eigenvalue of the instruction?
Yeah, isn't that subtle? Isn't that weird? How does somebody want to find the eigenfunctions of an annihilation operator? Because the annihilation operator is non-Hermitian. And why the annihilation operator? Why not the creation operator? Well, if you try to find the eigenstates of the creation operator, you run into problems. The eigenstates are non-normalizable. It doesn't make any sense. So here, creation and annihilation are not symmetric. You have to pick the annihilation operator. Colin, my gut feeling is that somebody found it in a different way. I mean, the person who popularized those states was Roy Glauber, and he got amply rewarded for that. And I think you define coherent state as some form of superposition state. Maybe people figured out if you take a superposition state of number states that this has special properties, that this is a minimum uncertainty state, which is as close as we can go in quantum physics to obtain a classical electric field. So I think maybe people found it like that, and then they say, hey, but there is another operator definition, eigenstate of the annihilation operator. I'm 99% certain, but maybe you can ask Roy Glauber when he comes to a COA seminar if he discovered coherent state as eigenstates of the annihilation operator. I don't think so. Other questions? So what I want to, what sort of the theme of the end of last lecture and today is that the coherent state is a complex number. The coherent state has a time evolution. It moves in a circle, and this is really the phasor of the electric field associated with it. So coherent state, the alpha value is directly related to an electric field. That's why why this state is closely related to the classical limit of the electromagnetic field. So we discussed some properties of the coherent state. We looked at the fluctuations and showed that it's a Poissonian statistic. And then we use now, well, once you define something, you can use it as a tool. We are now using the coherent states to look at any other quantum state of the electromagnetic field, any statistical operator which describes photons, by forming the diagonal matrix element of the statistical operator with alpha. If you just want to sort of think about it intuitively, alpha is like the best description of an electromagnetic field. So if you write down this, we ask, what is the probability for an arbitrary quantum state described by an arbitrary statistical operator? What is the probability that the electric field is alpha in a complex description? So that's what those quasi-probabilities are, Q of alpha. And we immediately looked at some examples of quasi-probabilities. We showed that the vacuum state is sort of an area, it's a Gaussian, and the area is it's an area, I don't know, forgot the prefactor. It's on the order of 1 or 1/2. We realized that thermal states are also a Gaussian, centered at the origin, but it is a much wider distribution, so thermal states have sort of much more uncertainty in the electric field than the vacuum state. And then we looked at the coherent state, and now, of course, when we looked at the coherent state, we realized that coherent states are maybe not as wonderful as I try to make you believe. They have some nasty properties, and that is when you ask what is the probability, the quasi-probability of the coherent state to be beta, naively you would expect a delta function, because when you ask what is the probability of a momentum state to be p0, if you have a momentum state p0, it has a delta function at p0. But here it's not a delta function, it's a Gaussian of standard deviation. I think the standard deviation here is what is it, square root 1 over square root 2? Because the Gaussian has usually 2 times sigma squared. And since the denominator is unity, so the standard deviation of 1 over square root 2. And that showed us that the coherent states are not orthogonal. You have to be a little bit careful. It's not your standard basis set. It's an overcomplete basis. So therefore, the coherent state is not a delta function in the quasi-probability. It's a little bit blurred circle with an area on the order of unity. And you have some homework assignment to look at it. So in some way, how you should look at it is that if you see some quasi-probability distribution, the distance from the origin, this is the absolute value of the electric field. The phase here is almost 45 degrees, but if you look at this uncertainty, you would also say, well, the phase is uncertain to within this angle. So you can pretty much read the uncertainty in the total electric field, the uncertainty in the phase. You can read pretty much everything you want from that diagram. Now, when we look at a number state, well, you often know in quantum mechanics, number and phase are complementary. If the number of photons is fixed, you know nothing about the phase. And indeed, the quasi-probability of a number state is a ring. It has no phase. It has completely random phase over the 2 pi circle. The energy is sharp of a number state. Since the energy is E squared, you may have expected sort of a delta function in the radial coordinate, but what you get is also something blurred on the order of unity, and I want to say something about that in a second. Finally, we discussed the time dependence, and the time dependence is very easy. After all, we're dealing with an harmonic oscillator, and in a harmonic oscillator, if we have a plane of x and p, symmetric and antisymmetric combination of A and A dagger, in this plane, in a harmonic oscillator, the quantum state is just rotating, circular rotation with omega. And indeed, we showed that when we apply the time evolution operator, and some of you were right, of course, with a minus sign, it moves with e to the minus I omega t, and therefore everything rotates in a clockwise way. Now, we discussed the operator of the electric field, and in this quasi-probability, we discussed the operator of the electric field, and I hope you remember that in the analogy with the harmonic oscillator, the electric field was A minus A dagger, and this is the momentum operator. In those quasi-probabilities, and we will see more about it, something which is sharp in momentum is a sliver parallel to the x-axis, so therefore you can regard the vertical axis, which is the imaginary part of alpha, as the momentum axis, and you can regard this as the horizontal axis as the x-axis. So therefore, since momentum is electric field, you always get the electric field by projecting onto the vertical axis. And if you project this fuzzy ball, you get a value 0 with some uncertainty. And if this quasi-probability starts to rotate due to the time evolution, we get an oscillating electromagnetic field, almost classical, except for that fuzziness. So that's where we want to continue. Any questions about that? Yes?
Why is there no phase fuzziness in the ET?
No phase fuzziness. There is a phase fuzziness. For instance, if you would say the phase is determined by the zero crossing, you don't know exactly when the zero crossing happened, and that corresponds to an uncertainty in the phase. Trust me, everything is in this diagram. Now, there are two things we want to continue. One is I want to show you that the coherent state is a minimum uncertainty state. The product of delta x, delta p is just, is it h bar or h bar over 2? One of the two. So it's a minimum uncertainty state, and therefore you can never have a quantum state which is less fuzzy than the coherent state. So this fuzziness here is the intrinsic uncertainty of quantum physics. So that's what we want to discuss today. But then we will immediately start with non-classical states, and that is, well, if this area is determined by Heisenberg's uncertainty relation, what can we maybe deform the circle into an ellipse, and these are squeeze states of light. So that's an outlook. That's what we want to do in the second half of the class. But before I do that, I want to be a little bit more accurate about quasi-probabilities. And this is almost like a disclaimer now. Just to give you the bigger picture, what we want to achieve with those quasi-probabilities, we want to do what phase-space density is in classical physics. We have a coordinate which is x, a coordinate which is p. And you can often describe a classical system if you know the phase-space distribution, if you know the probability that a particle has position x and momentum p. So all this is about phase-space densities in a way, let me just kind of probability of x and p. Of course, writing it down, you immediately see the problem. In quantum mechanics, you cannot measure x and p simultaneously. These are non-commuting variables. So therefore, what happens is, if you now define a phase-space function, which is done in quantum mechanics textbooks, you can actually do it in 3 different ways. And the 3 different ways are Q, P, and W. The definition, I don't want to go through the mathematical subtleties, the definition of those functions involves the operator definition A and A dagger, or, which is equivalent, the X and P operator. If you define something in units of x and p or a and a dagger, you can have a product which is fully symmetric in the ordering of xp, which is anti-normal or normal. So in other words, the order matters. And you have 3 choices. In an operator product, you can have symmetric ordering, which means not xp, but xp plus px, then it's over 2, that's symmetric. You can have an ordering which is called normal and one which is called anti-normal. Ordering of operators in the operator-based definition. Of course, if we have 3 choices, you would say, which one is the best? Which one is the winner? But the fact is, all 3 have their advantages and disadvantages. So they all have pluses and minuses. The reason why I picked for the cause Q of alpha is that it's a real probability. It's always positive. It is a diagonal matrix element of a statistical operator, and this has to be positive. So it's a real probability. The other guys, P of alpha, can be positive or negative, and also W of alpha can be positive and negative. So if you use the P alpha distribution, statistical operator can be written like this. And as a result, the coherent state is now not this Gaussian, it doesn't have this Gaussian distribution as a quasi-probability. It's what you want, what maybe some of you wanted to see right away, it's a delta function. The probability of the coherent state alpha has a delta function peak at alpha, which is sort of nice. And the number state is not sort of a ring of a finite radius. I just mentioned to you the number state. You would naively expect the energy is sharp, the square root of the energy is the electric field, shouldn't it be sharp? And indeed, it is sharp. It's actually worse than a delta function. It's a derivative of a delta function. But at least here, in the probability P, which is also called the Glauber-Sudarshan P representation, you get sort of the delta function which may be very natural for certain purposes.
Since the coherent states are always included, you can express one in terms of the other. Is that P unique?
It is unique by some symmetry choice here. Yeah, so that's the advantage of it, that I'm not going into the mathematics, I'm not giving you the definition, but the way how it's defined, it is unique, it can be written in such a way, and the way how the quasi-probabilities P, the P representation is defined, you get a delta function at the coherent state. And finally, W stands for Wigner distribution. And the Wigner distribution is something you actually find in most quantum mechanics textbooks. The Q and P distribution are more common in quantum optics, but the Wigner distribution has the advantage that the projection on the x and y axis are indeed psi of x square, psi of p square. So you get actually the x wave function and the p wave function. So now, as a full disclaimer, if you want the electric field, which is the momentum of the harmonic oscillator, which is the electromagnetic field, what you really want to project is the W function, because for the W function, the Wigner function, the projection is exactly the momentum distribution in the electric field. So the Wigner distribution is closest to the classical phase space distribution, as close as you come without violating commutators. But of course it has the disadvantage that it has negative values, and try to explain to your next neighbor what is the negative probability. Some people actually say negative probabilities bring out the non-classical character. And I know in our field, in AMO physics, a few years ago, during my lifetime, there were really attempts to use quantum state tomography and measure for the first time a negative Wigner distribution and show that to the world. So that meant something to a lot of people. Anyway, you can read about it in quantum physics textbooks. All I want you to know is to know about it, but then also just relax. In the bigger picture, all the three distributions are the same. It's more sort of on the level of whether something is a delta function or has Witt's unity. So sort of on that small scale, it matters. But if you map out something on a bigger scale, they are all related to each other. And for the rest of today and the next class, when I show you those phase space distribution, when I say I project onto the vertical axis to get the electric field, I'm not completely rigorous which of the three functions I've really chosen. Any questions? Okay. So I promised you, and this is what we want to do now, is we want to understand in more depth the fluctuations, and in particular, I want to show you that coherent states are minimum uncertainty states. So by identifying the vertical axis with P, the horizontal axis with X, we immediately expect that we find a result related to the Heisenberg uncertainty principle, which says that the width in P and the width in Q has to be larger than h bar over 2. And we are mainly talking with light about the photon creation and annihilation operator. But just as a reminder, the momentum and position operator are symmetric and antisymmetric combinations. So let me just call those prefactors Q naught and this one P naught. We can then immediately, by just using elementary commutator, calculate what are the expectation values in a coherent state for P, P square, Q, and Q square. For P, it is the P operator is A dagger minus A. if we act with A on alpha, we get alpha, because alpha, the coherent state, is an eigenstate of alpha. With A dagger, well, with A dagger, we act on the left-hand side, and we get alpha star. Well, with P square and Q square, you have to use one or two more steps to get rid of the products, but ultimately you can express all that just in powers of alpha, alpha square, alpha star, and such. So what we want is, we want to find out what are the fluctuations delta Q, delta P. Just as a reminder, delta Q square is, of course, Q square average minus Q average squared. And Q square average and Q squared is what we have just calculated. So actually, let me leave it in as a reminder for you. Q square minus Q average square, the square root of it. And what we find is that it's square root h bar over 2 omega, and for delta P, it is square root h bar over omega 2. And what we verify, that indeed, for a coherent state, the product of the two is Heisenberg uncertainty limit. So therefore, coherent states are minimum uncertainty states. And maybe, Colin, to address your question, I could imagine that coherent states were maybe invented by simply saying, we have an harmonic oscillator, we want to find the minimum uncertainty states. The minimum uncertainty states for which the uncertainty in x and p, when expressed in natural units, is the same. In other words, the coherent state is the solution to the following question. If you plot the quasi-probability distribution, you give yourself an uncertainty area. The horizontal uncertainty is delta Q. The vertical uncertainty is delta P. And the minimum uncertainty state means that the area of the two uncertainties, the area of the shaded region, delta P times delta Q, is h bar over 2. Or if I want to rewrite that in the real part of alpha times the uncertainty in the imaginary part of alpha for the quasi-probabilities, then this is 1/4. Okay, so what we have learned is that, just one sec, we have learned about one way to characterize uncertainties, the quantumness of the electromagnetic field, by looking at the uncertainties in the x and p variable, and that led us to minimum uncertainty states. Now, I want to now introduce to you two other ways of characterizing the uncertainty of quantum states of light. One is we can ask what are the fluctuations in the photon number. Right now we have asked what are the fluctuations in the electric field, but the next question is what are the fluctuations in the photon number? Or we can ask what are fluctuations in the intensity when we measure the intensity of the electromagnetic field. So let's do that. The fluctuations seems I've lost my lines. Okay. Okay. So the fluctuations of the intensity are usually expressed by the second order temporal coherence function. And that's what we want to introduce now. Yes, this is the second order temporal correlation or coherence function. What I'm always encountering in this course is I would just like to immediately tell you how it is defined in terms of A's and A daggers. It's simple, it's quantum mechanical, it's exact. But I always feel that if you want to really appreciate the quantum character, you have to know the classical description first. So I want to first tell you what is the second order coherence function for classical light, which has a classical description, and then you see what is the difference for quantum states of light. So the classical description is you measure the intensity of light. Well, you're just sitting here, you receive light from a light bulb. You measure the intensity at time t. You measure the intensity time tau later, and then you form the product, and you normalize it by the average intensity squared. So if tau equals 0, it's nothing else than the intensity squared average divided by the average of the intensity squared. So this is the classical definition, G2 of tau. And I've left the proof to the homework to show that the classical G2 of tau is always larger than 1. Well, it's pretty much what you show is for tau equals 0, it means, you know, I square average is larger than I average square, which is of course always the case, but you can show that this is also the case for finite tau. So quantum mechanically, we will see that the G2 function is not necessarily larger than 1. It can be smaller than 1. And that's actually an interesting, you can say, litmus test for the quantumness. If you generate states of the electromagnetic field, Fock state, photon number states, we see that in a moment, and they have a G2 of tau which is smaller than 1, you know it is not possible in any way to associate an intensity of the electromagnetic field with that photon state, because whenever you can associate a classical intensity with that and use a classical intensity to calculate the second order correlation function, you get something which is larger than 1. So often, therefore, again, when people want to show we really have now non-classical photon states, they show that G2 of tau is smaller than 1. This is similar to what I said before when you want to show that you have non-classical light, you do quantum state tomography, measure the Wigner distribution and show that the Wigner distribution has negative quasi-probabilities. That's again something which is classically not possible. It's only possible if you have a truly non-classical state. Yeah.
So in the definition of G2 classical, the expectation values mean averaging over time, not over like ensembles of IFT?
Okay. That's, yeah, you can average over ensembles, so you can have, 1,000 light bulbs, switch them all on, and then measure at a certain time that. But what we assume here is that the light bulb is on continuously, so things don't really depend on T. So you can set, I've implicitly taken care of it by defining the G2 function only of tau and not of T and tau. You assume any time is the same because it's a distribution, it's an ensemble in steady state. But it's a sort of the same story again and again. In classical physics, you can determine an ensemble average by taking an ergodic system and observing it at many, many times. And then the idea is that one system, as time goes by, will sample all possible states. Or you can prepare many, many identical systems and do more what is an ensemble average. So in other words, you would actually think if you switch on a light bulb with a stable power supply, that the light emitted by the light bulb will go through all possible quantum states as time evolves. And therefore, the temporal average is equal to the ensemble average. Okay, so now so how do we generalize that to quantum mechanics? Well, one possibility would be that, okay, first of all, for quantum mechanics, we have to use operators. And one choice would be that, well, you say the intensity of the electromagnetic wave is proportional to the electric field squared, and you want to use the operator for the electric field squared. Now, there is a little bit of a problem, because what we really mean quantum mechanically by G2 of tau is we measure the intensity now and a little bit later. But measuring the intensity really means absorbing photons, because the only way how you can measure the intensity of light is with a photomultiplier. It makes click, the photon is absorbed. And this is not fully described by the electric field. Just assume you have no photon, you are in the 0-point state of your harmonic oscillator, and your E square has 0-point fluctuations. So what is more closely related to an experiment, how you measure the correlation function, is you want to look at something else, namely at the probability of absorbing two photons. So you start with an initial state. You annihilate two photons, and then you have a final state. But if you are only interested in what is the probability you want to characterize your initial state, you may want to sum over all final state. And this is your total probability that you can absorb two photons out of an initial state. But since you can sum now over all final state, this turns into, now I could put for you in as in, the final state as a complete basis, but I can also take it out. So this is what we get. So this suggests that experiments where we look at two subsequent clicks of a photomultiplier where we determine the photon correlation, that this is measuring a correlation function which for quantum states of light should be defined as the expectation value of A dagger, A. And now we have to normalize by the probability squared of absorbing one photon, which is A dagger A expectation value squared. I just try to be a little bit sort of too motivated. In many, many textbooks, the discussion would start with this expression. You ask, where does it come from? And you realize, yes, for some measurement with photomultipliers, that's what you measure. But I wanted to sort of show you how it is related to the intensity correlation function defined classically. Cody?
But this looks like it's constant in tau. Which doesn't really make sense intuitively to me. Because at least classically, it shouldn't be constant in tau.
Okay, that's the next thing I wanted to say is I've swept here. I mean, I just wanted to give you the structure of the operators and not get sort of distracted by discussing time. I've dropped the time argument here. But the fact is, that as long as we limit ourselves to a single mode of the electromagnetic field, a single harmonic oscillator, things are independent of tau. In other words, G2 of tau equals G2 of 0 as long as we are dealing with single mode light. You can actually say, and that sort of tells you where the fluctuations come, if G2 of tau changes, it comes because you have several modes of the electromagnetic field which as a function of time constructively and destructively interfere. But if you have a single mode, in a single mode, I mean, what is a single mode? It's just a sine wave and nothing happens as a function of time. It's constant.
So those modes go inside.
You know, I'm squeezing a textbook of quantum optics into two classes, and I want to give you sort of the ideas and the concepts. What I've sort of mixed up here deliberately is I've given you the classical definition of an intensity correlation function, which is, the famous Henry-Brown-Twiss experiment, and you have correlations as a function of time. Then I've motivated how this should be defined for quantum states of light. But when I transitioned to quantum states of light, I decided to deal with only one mode of the light. We should now sum over, I should put double or triple indices on all the alphas for polarization, for spatial modes, for different frequencies, and we sum over all of them. But instead what I did is I wanted to just show you the simple case, and I think you will be thankful for that in your homework, that you only have to deal with the simple case, that you only have to look at A's and A daggers and the operator algebra for single mode, for single harmonic oscillator. But what we lose, so to speak, here is there is nothing interesting going on in time. I've already told you that for a single mode, all these quasi-probabilities, they just rotate in a circle. So the time evolution of the system we are describing right now is completely boring. It's really a rotation, and if you would rotate your head at omega, nothing will happen, and this is exactly what you see here. So you find everything you want for coherence time. Coherence time is the time for two modes to get out of phase. But if you have one mode, there is no coherence time. And when you find for classical light that that a G2 function has a peak which decays with the time, it is the time for modes to get out of phase. But in a single mode picture, this is absent. Anyway, what is important now for the discussion of quantum character of light is really, we find that in a single mode picture. So I want to show you now, or at least give you the summary of the results, which can be very easily derived because the math is very simple of those operators, that we are now with that definition, we have G2 functions which are no longer following the classical constraint that G2 has to be larger than 1. We find now G2 functions which are smaller than 1. And this sort of tells us now where do we find the most non-classical behavior, namely when G2 of tau is as small as possible. Okay, in your homework, you will show immediately that the G2 function is related to number fluctuations. And it's related to n average and n square average. Let me just write that down. It's independent of tau. And the reason is we have now limited ourselves to just one mode of the electromagnetic field. Factor. Just give me one. Yep. Okay, so we are back to, we started with intensity fluctuations, but for a single mode of the electromagnetic field, we are back to photon numbers. So what we are now expressing with the G2 function are in other words, just fluctuations of photon numbers. So before I want to in a minute draw you a little bit a table. What are the fluctuations in the photon number for the states we have encountered? The number state, the Fock state, the coherent state, and the thermal state. And we want to characterize those quantum states of light by the G2 function. And actually, I can drop the time argument or set it to 0. But let me first make a reference that G2 can now be smaller than 1. So G2 for a single mode light is nothing else than function. When you know what is n average and n square average, you know your G2 function. There is another quantity which we often use to characterize the fluctuations in the photon number, and this is called the Fano factor. The Fano factor is wants to compare the fluctuations n square average minus n average squared. These are the fluctuations. The classical fluctuation, well, when I say classical in the simplest case are Poissonian fluctuations. So maybe we want to normalize the fluctuations by Poissonian fluctuation. So for Poissonian statistics, what I just wrote down would be 1. And well, if we now subtract 1, we have the situation that the Fano factor which is positive is super Poissonian, more fluctuation than Poissonian, and the negative Fano factor is sub-Poissonian. So with those definitions, we can now compare the different states of light we have introduced. We started out with black body radiation, thermal radiation. We defined coherent states, and the harmonic oscillator description naturally gave us harmonic oscillator eigenstates, the number states or Fock states. So there are three ways to characterize it. They are all useful. One is we can look at n square, we can calculate the Fano factor, or we can calculate G2 of 0. For the coherent state, remember the coherent state is as close as we can come quantum mechanically to the ideal of a pure electromagnetic wave. It has a Fano factor of 0. This means it's Poissonian. The G2 function is simply 1, which is the lowest classical limit. So those two tell you that a coherent state is sometimes what you think what comes out of a laser is an ideal electromagnetic wave which has no temporal fluctuations in the intensity, therefore G2 is 1. And the photon number is Poissonian distributed. And that means that n square is n average times 1 plus n average. We actually discussed it earlier. The thermal state is quite different if you use, kind of plug together the results we have obtained. It has a Fano factor of n bar. So this is super Poissonian. If the occupation number n is large, you have fluctuations which are much, much larger than Poissonian fluctuation. The G2 function is 2. It's sometimes called thermal light. Chaotic light has a G2 function of 2. Laser light or coherent state has a G2 function of 1. And n square average is n bar 1 plus 2 n bar. Okay, but now finally, maybe the most interesting state from the perspective of non-classical light, of quantum light, is the photon number state. Well, for the photon number state, the number of photons is an eigenvalue, therefore n square average is n average squared. The Fano factor is -1, sub-Poissonian distribution, and the G2 function, which classically cannot go below 1, is now n minus 1 over n. It is smaller than 1. And you see immediately that the biggest violation for G2 is to go to -1 for the case of a single photon state. Any questions? The G2 function? No. If you put in, wait. Yes. Gosh. I double check. I'm a little bit confused, but yeah, at least it's consistent now. I'm not sure if it's right, but it's consistent. And by the way, if there is a question I sometimes make a question mark in my notes, and when I post the notes, or when I post, maybe not when I post the notes on the next day, but a few days later, the question marks are eliminated. Just as an example, last class there was some relation for which I didn't remember how the derivation was done. When I post those notes today, the derivation is now in the notes. So if you want to, I'm not announcing it separately, but whenever I have a question mark in class and I don't think it's worth an extra announcement, it is fixed in the post-it notes and you find the information there. Okay, so this is now drawing our attention to the single photon. And this is our next subsection. I mean, this shouldn't come unexpected. If we want to, emphasize, if we want to emphasize the difference between quantum light and classical light, where does it come from? Well, it comes from the quantization of light, it comes from the photon character. It comes from the fact that light is not a continuous stream of energy, it comes quantized in photons. So the granularity of light due to the photon character is, of course, most pronounced for single photon. For instance, when we define the G2 function as the correlation of detecting a photon and detecting another photon, well, if you have only one photon, you find one photon, and the next photon, there is no photon to be detected. So the probability of detecting two photons is 0, and that only happens when you go down to single photons. So this is when certain fluctuations are most pronounced because the energy sort of is dependent on a single photon. Let me first address one misconception. You can say, well, let's just use a coherent state. And we talk about the attenuator, the quantum attenuator, with all its operator beauty. Probably not today, but in the next lecture. But let me already sort of prepare you for that. When you have a coherent state, when you have a laser beam, you can put in an attenuator, and your laser beam gets weaker and weaker and weaker. But it stays a coherent state, and I will prove that to you very soon. So you can now say that you take your coherent state and you attenuate it down, that there is only one photon left. Is that a single photon state? The answer is no. It is an attenuated coherent state. Coherent states, as I've just shown you, are very classical. They have always Poissonian distribution. They have always a G2 function of 1, and attenuation is not changing it. Attenuation is preserving that. So now I want to show you explicitly why an attenuated coherent state may have an average photon number of 1, but it shares nothing else with a quantum state of 1 photon of n equals 1, a Fock state. So a coherent state with an expectation value of 1 photon is not a single photon. And this can be, for instance, expressed by looking what is actually the probability, if you have such a coherent state, to find 1, 2, or 3 photons. Well, the probability to find 0 photons, no photon at all, is actually 1/3. So the probability to find 1 photon or to find 0 photons is the same. The probability to find 2 photons is 0.18. So here you have a probability of finding a photon and correlating it with the next photon click. And you have even, on first sight, a surprisingly large probability to find 3 and 4 photons. So in 2% of the cases, you will find 4 photons. Whereas in contrast, the Fock state with quantum number n equals 1 is an eigenstate of the number operator with eigenvalue n equals 1. So that tells you that if you want to get an n equals 1, if you want to get a single photon state, you cannot just use a strong laser beam or a strong light source and attenuate it. You have to work with something which genuinely creates only 1 photon without any ambiguity, without any fluctuations, without any possibility of creating 2 photons. And I would actually say over the last 10 or 15 years, the creation of single photons has been sort of a small cottage industry, because single photons are often needed for protocols in quantum computation, for experiments which really require accurate quantum state preparation of light, and in particular non-classical light. But of course, there are ways how you can get single photons, and this is, well, you start with single atoms. If you have a single atom in the excited state, it can emit only 1 photon. So, in other words, you cannot, we often don't, or usually we don't have the tools to prepare a single photon, to take a single photon out of, many, many photons and store it separately. But what we can control is single atoms. We can prepare single atoms, and then we can make sure that single atoms create single photons. It's a little bit a way that, we cannot control the bullets which are fired, but we can control the guns, and we make sure that each gun can emit exactly 1 bullet. So that's the way how we can create non-classical states of light. Yes, so let's now look for those single photons at the quasi-probability distribution. So we obtain the quasi-probability distribution by taking the single photon state and projecting it on a coherent state. You remember, it's higher up in the notes, what the coherent state alpha is in a Fock state basis, in a number basis. And so we are just picking out n equals 1. And this was nothing else than alpha squared times e to the minus alpha squared. So therefore, in these diagrams with the real part and imaginary part, if I plot the quasi-probability distribution, we get a ring. The ring immediately tells us that there is no phase defined. All phases are equally probable. And that also means if you don't have a phase, the average value of the electric field is 0. Since the creation of single photons is essential for studying non-classical light, but also since it's a very active frontier of our field. Actually, one of the leaders of this field is Professor Vladan Vuletic here at MIT. Let me at least give you a taste how to create single photons. I already gave you the major ingredient, namely it's about, it involves single atoms, but it's a little bit more demanding like that. So you want to take one atom or one ion, but the problem is if the atom or ion emits the light, it can emit the light into all directions. And therefore, you have a single photon afterwards, but you have many, many different spatial modes, and in any given mode, you do not have a single photon. So therefore, what you have to add to the single atom or single ion is you have to put it in a cavity, and then in the limit of a very, very high finesse cavity, the probability will be very, very high that your photon is emitted into the mode of the cavity and it is not emitted perpendicular into other modes. But that itself is not yet sufficient because you have a single photon, but you also want to know when does the single photon arrive. You want to do experiments, you want single photons on demand. So one option is that you prepare your atoms in the ground state. You take a pi pulse, which with 100% probability excites the atom to the excited state. And then within a natural lifetime, or maybe even in resonator-enhanced inverse natural line widths, the single photon is emitted. So therefore, you pump the system, and then you know within the next few nanoseconds, your cavity mode will have a single photon. The problem here is that you're dealing, you have to prepare single atoms, which is difficult. You have to couple them to a high finesse cavity. There is technically another approach where you use many atoms. So if you have many atoms, you no longer have, a single gun, so therefore you can get several photons. But the singleness in photons comes because the photons are now heralded, they are announced. And the idea is the following. If you start with a state 1 and you have an excited state and you have a pump pulse, you are now, if you have many atoms, you have a much higher efficiency of pumping atoms to the excited state, because if you have n atoms, it's n times more efficient. But now you take the following situation. You wait until there is a Raman transition, until you detect a photon for Raman transition where the excited state decays to the state 2. At this moment, you know I have now one atom in state 2. So in other words, you're not starting with single atoms, which is sometimes more demanding. How can you prepare the system? It has other disadvantages that n atoms have. I'm not sure if I should mention it, but with n atoms, they have a super radiant factor n. With n atoms, you can get an n times enhancement of emission into a single mode. So there are real massive advantages in working with many atoms, but now you know that one atom is in state 2 when you detect the first photon. And then you have the same situation which we had above. You can now take your system. Let me just redraw the level diagram. Excited state, state 1, state 2. You know now that you have one single atom here, and by using a laser pulse, you can excite it to the excited state, and then you observe the single photon 2. So in other words, the observation of the first photon tells you that your system is prepared with one atom in state 2, and then you can get a single photon out of it, which is the photon for the inverse Raman transition when you pump the system back to state 1.
Doesn't this rely on you being able to reliably prepare a single atom in another electronic state? Won't there always be some uncertainty as to how many atoms you prepare in that state?
There are some uncertainties, and what you are saying is correct. We don't have perfect single photon sources, and people characterize the fidelity of the single photon source. For instance, if you detect the single photon, you would say, now my system is ready to emit a single photon triggered by this pump pulse. And if you can get now a single photon in 90% of the cases, you publish a wonderful paper because you've set a new record for the fidelity of a single photon source. So people are really struggling with some of those uncertainties. But to involve, for instance, 3 levels is sort of an advantage because you're not limited by the preparation of a single atom, for instance. You can have many atoms. The atoms are always there. And the moment one atom is prepared in state 2, this atom announces itself with a photon. So it's sort of, it takes a lot of uncertainty out that the system says with the first photon, I'm ready now, I can emit a single photon, and then you get your single photon. Then you can gate your whole experiment to a time following the detection of the first photon, and for your gated time afterwards, you have very, very high probability of finding this photon. Or if you want, you can now do experiments with 2 photons. If you keep this laser on and pump the atom immediately back, you have actually a single photon here followed by a single photon here. It's sort of click, clack, and now you can do correlations between 2 different single photon states and such. It's a very rich frontier of our field. You had another question?
Yeah, is this also within a cavity now, like the single photon detection in the first step?
Yes, actually, all that. I mean, these photons, the wavy lines, are emitted spontaneously. Spontaneous emission, pretty much by definition, goes into all possible spatial modes, and the only way to control the spatial mode is with a cavity. What I don't want to go into details, but those who have an understanding of that, is the following. If you have n atoms, and you prepare one atom here in state 2, you do not know which of your n atoms is prepared. So you have n indistinguishable possibilities. And if you have n indistinguishable probabilities which atom you have prepared, the emission of the photon back is n times enhanced. So therefore, you have actually a system which has an n times stronger coupling to the cavity. So having n atoms makes it much, much easier to construct a high finesse cavity. You get sort of this super radiance increase of the strong coupling for free. And this is why there are many reasons why you do not want to work with a single ion or a single atom. It's possible for very fundamental experiments. People have shown that it can be done, but technologically, it's much easier and much more robust to work with many atoms. But then you need sort of, the many atoms have to tell you when one atom is prepared to emit now a single photon. If you're interested in this subject, talk to the students in Vuletich's group. They're really the world experts in that. Okay, finally, we're not really getting to squeezed light. We start with squeezing the light tomorrow. The last thing in this major section is the famous Henbury-Brown-Twiss. Experiment. This was a landmark experiment done in the 1950s, and it was the first experiment which really looked at G2 functions correlations, which one could say was the beginning of quantum optics and modern experiments with light. Probably until then, light was just an electromagnetic wave. People regarded it as boring. But by measuring now correlations, people realized that it's an interesting object to study. I want to just go over the basic scheme. You will look at it a little bit more closely in your homework assignment. So the idea behind an Henbury-Brown-Twiss experiment is that you have a light source and you want to characterize it. So the light source emits light. And now this is important. Whenever you want to detect two photons, you want to figure out, is one photon followed by another photon? Technically, you cannot do it with a photomultiplier, because when a photomultiplier clicks, it needs many nanoseconds for the photomultiplier to read out the signal and recover, to recharge up its electrodes and be ready to detect the next photon. So therefore, when you want to find click, double clicks in the stream of light, you have to involve a beam splitter and involve two photodetectors. Sure, you now need an adequate description, but in principle, you can now find two photons which are only a few picoseconds apart, because the first photon is observed by the first detector, and the second photon is detected by the second detector. Sure, you would say, what happens if in the beam splitter both photons go detector one? Well, that's tough luck. That's you take one chance in two that the two photons go to the two different detectors. But the beam splitter has to be part of your experiment, has to become part of your description, and this is what you do in homework number 1. So what we are asking here when we measure the G2 function, let's assume at tau equals 0, we are reading out a signal, and what we are using is a coincidence detector. We are looking that in a very small temporal window, two photons are detected simultaneously. Well, this is the quantum version. The classical version is the G2 function is the product of the intensity at times t times the product of the intensity at time t plus tau. So what you would do here in this circuit, you would take the signal from this detector, the signal from that, and multiply the two. This is how you determine I of t times I of t plus tau. So whether you do it in the classical domain or whether you do it in the quantum domain, this is the way how you experimentally measure the second order correlation function. In the classical limit, you don't have to worry about it. The classical limit is always the limit of high intensity. So at any given time, you have a ton of photons. And then at beam splitter, half of the photons go left, half of the photons go right. You have an equal splitting. You have exactly half the intensity in the left arm and the right arm after the beam splitter. So there is no problem at all with the quantization because this is the classical limit. So classically, you can say, I shouldn't say photon, I should actually say intensity. The intensity splits equally. And if you do the measurement with the coincidence detector, you find the difference between the G2 function, which I discussed earlier, that the G2 function is 1 for coherent light or laser light, and the G2 function is 2 for thermal light. That's actually the only way how you can distinguish a light bulb from a laser beam. If you put a light bulb into a cavity or couple the light from a light bulb into a fiber, the light becomes spatially a single mode. If you put a very narrow spectral filter or Fabry-Perot cavity, the light becomes single mode in frequency domain. So when you take a light bulb and spatially and spectrally filter it, that it is single mode, in terms of the mode, it is single mode as a single mode laser. But it is a correlation experiment which shows you that you started with a thermal source. It has a G2 function of 2, and you can never get rid of it, whereas the laser beam has a G2 function of 1. Okay, so this is the classical version. In the quantum version, especially when we have a single photon, the photon can go to only one detector, and that means for this extreme case of a single photon, the G2 function is 0. Anyway, you will look at those situations in more detail in your homework assignment. Yes?
So if you looked at different times with tau non-zero, then even a single mode of a Planck state would have a finite G2, I think, right? Because there would be some probability to detect the photon at one detector and then at a later time, or at the other time.
Single. We have to be now a little bit careful. If we have a single mode Fock state, there's only one photon. And once this photon is detected, we have vacuum, we have no photon left. So what may be confusing here is, on first sight, is that the way how the experiment is done and has been historically done, it's not done with Fock states, it's done with a light source and a continuous stream of photons. So Hanbury-Brown-Twiss experiment, he looked at light bulb, or he looked at starlight and such, and determined the intensity correlation. He couldn't do the experiment with lasers, but now we do it with a laser beam, and we find that G2 is 1. But in those situations, we actually do not have the way, we have a beam which is a stream of photons, and it requires a little bit different description. In other words, when I have a coherent state, a laser beam is always replenishing the coherent state. The laser beam preserves the electric field, whereas, strictly speaking, the way how I described it for pedagogical reasons is you have a cavity which is filled with a coherent state alpha, and then you start analyzing that. But in other words, what we have focused in the simple description is that we have a quantum state which is prepared. It's a closed system, and now we do our detection. The experiment, how it is done, is often done as in an open system, where you couple the system to a light source, which is always replenishing your experiment. So you have to be careful, especially with a single photon. I think in essence the experiment would be done with a single photon light source, but the single photon light source has a high repetition rate. It's sort of, I showed you how to generate single photons. You have sort of an heralded single photon. You know the single photon comes now, you do the experiment, and then you repeat it again. And what you have is you only look at one single photon bunch at a time, and then you find indeed that during that temporal window you will never find a second photon. So this may happen in a few nanoseconds, then you wait a microsecond and the next photon arrives. And it doesn't, of course, if you would now describe your light source, what is the G2 of tau, and tau is a microsecond. And the microsecond is the time between the first single photon burst and the next single photon burst. Now you will find that your G2 function is not zero. But this is then related to the repetition rate of a single photon and not to the single photon itself. I think you got the taste. Your homework is really simple. You just deal with a closed system. You look at a quantum state at a time. But if you map it onto a beam experiment, you have to think about it. What does it mean to have a replenishment of the quantum state? Any other question? I know I have to stop, but...
We just,
yes.
In the beam splitter, the other port of the beam splitter should do some stuff, right?
Yes, actually, this will keep us busy for a while, that even if we do not put in any light, we put in the vacuum state. And you will find that the description of the beam splitter in the quantum picture is incomplete unless you specify that your beam splitter is coupling in from a different mode the vacuum state. Yes, this will be very important, and we'll cover that in its full glory. Timo?
The way you can distinguish from a thermal state and a coherent state is through the G2. So from an experimental perspective, could we do most of our experiments if we just had like thermal sources that were very single mode, so to speak?
Oh yes. I mean, all the laser cooling, all the molasses, all the absorption imaging, all that would work if you had a single mode thermal source. Let's face it, we say we use lasers for everything we are doing, but the only property which distinguishes a laser from a thermal light source, we are not taking advantage of it. Of course, practically, if you take a thermal source and filter it down to a single mode, you will be left with only a few photons. You cannot create an intense enough single mode light source unless you use stimulated emission into a single mode, and that's a laser. Colin?
The correlation function for example, an LED light, that's not really a thermal source. It's not described by Maxwell-Boltzmann distribution. That'd be closer to something for like a laser, even though there is no cavity per se.
Well, LEDs in some limit are quantum objects. So actually, do you know what the G2 function of LED is? Does it become laser-like, or does it become even anti-bunched? Because if it's a relaxation mechanism. So anyway, what Colin says is there are actually more than, more different light sources than just the laser and the thermal light source. There are LEDs or semiconductor devices which provide photons with interesting statistical properties. I don't know exactly what, I've heard about it, that LED light sources have some special properties, but I don't remember which is the one. Okay, we have to stop. I see you on Wednesday.